So there have been some questions and concerns and confusions about all these factors affecting enzyme catalyzed reactions. So let me try to help you guys through this a little bit more. So looking here at describing how, let's just look, we'll concentrate on this substrate concentration. So how concentrations of substrate are going to affect the initial rate of the reaction, and then explaining that. So this right here being linked to this concept of this maximum initial rate of the reaction, or this Vmax. I know this is something that's new for everybody, so we'll address that. And then coming down here to explaining this concept of enzyme saturation, right? This stuff down here in 3B, we'll do that in a separate screencast. So this is factors affecting rates of enzyme catalyzed reactions 1A, and then I'll make a 1B where I'll try to address the temperature and the pH stuff. Okay. So we had seen this image in a previous screencast, and this is just the mental model of enzyme, active site, substrate fitting together in this induced fit right here for a brief moment in time. The reaction happens, and then you churn out product, and the enzyme regenerated there. So in the lab, what we're doing is that this substrate was, of course, hydrogen peroxide, and these products, one of them was water, and the other one was oxygen gas. Keeping in mind, of course, that enzymes also do the reverse of this reaction, or reverse of these sorts of reactions. Instead of breaking things down, they could indeed build them up. So putting these two things together and having, these arrows go the opposite direction, that's also a possibility, but not what we were seeing in the lab. So in the lab, again, some confusions as to what you're doing with the computer and what you're being expected to print out and talk about in the mini poster. So initial rates of the reaction are determined by measuring either substrate used or product made. We, in our lab, were measuring how much product was made per unit time, not how much substrate went away. So the graph that you're seeing on the computers was, of course, there was a time component to it in seconds. And then over here, since, again, we were measuring the product made per unit time, that was oxygen gas made, right? And we weren't measuring a volume of how much gas is made. Instead, we were sort of inferring the volume increase by measuring the pressure, right? And how that pressure in kilopascals changed over the time period. So when you set up your experiments, right, if this is time 0 and say 10, 20, 30, 40 seconds there, you were measuring that. It took you a few seconds to kind of get the lid on and get pressure then building up, and then you had, pressures sort of increasing thusly, right? And then you stop the reaction. Either the thing popped off and then your pressure would drop way down, or you decided to stop it in that time frame. So then what you were doing, or what you should have been doing, is then saying, okay, I'm going to take from 10 seconds to around here, and I'm going to look at that, and I'm going to get the best fit line through those points, and it sort of went off this way, and then it gave you this m value, or the slope, right, which of course is the change in the y over the change in the x, which is of course the rate, right, the rate of the reaction, meaning change in the pressure over the change in time. Change in the pressure over the change in the time is a rate of that reaction. So you were doing this, and let's say that this was at a particular substrate concentration, right? So you had this at, say, 3% hydrogen peroxide, that line, and you would do this whole thing times, say 10 trials, and then you would take the average x bar of those 10 trials and get then some sort of rate, right, for that 3% peroxide. What you're doing then is taking those rates that you measured in lab and then converting that, or not converting that, but then plotting that on another set of axes over here, where you have again, concentration of substrate in percentages here. And if this was where 3% peroxide was, and then your rate over here again being kilopascals per second, so how much pressure was changing. So you take this X bar rate, and that gets plotted right here, wherever that value happened to be. Y, you know, if it was that right here, you're going to get a point right there. And then you had the different substrate concentrations, right? Or whatever you were measuring. This could have been enzyme concentration, this could have been temperature, this could have been pH. You're doing, you know, separate lines there for each of those. So this graph over here, this is what is being ultimately reported out and goes on the mini poster. That said, let's talk about what's happening here with substrate concentrations and the explanation, the biology behind what's happening here, right? It's not so much biology, but logic as well. So let's pictorially take a look at this here, and we say that let's put in solution, in solution, we'll put 1, 2, 3, 4, 5 enzymes. So this is 5 enzymes in, let's just say that this is 100 milliliters of water. So this is a concentration of enzyme, right? So I've got this concentration of enzyme, and let's say we let this reaction run for, you know, 30 seconds. Right? We drop our substrate in, right? And that substrate is at a concentration of 2%. So substrate goes in, here are our enzymes. What is the likelihood that you have a substrate colliding with an enzyme, right? And so this is all based on collisions, number of collisions per second. Well, if the substrate is relatively low, what's the probability that one of these enzymes bumps into one of these substrates? Maybe relatively low. And so you're saying, okay, what the heck does the collisions have to do with anything? Well, you need to get the enzyme colliding with this substrate right here in order to get an induced fit. That's how this is all happening. You're assuming that all these enzymes and substrates are moving randomly in this solution, and you're waiting for these collisions to happen. Right? So the likelihood of these things colliding, relatively low, right? And you get these, but when you do get a collision, you get an induced fit. You then turn these substrates into products. So the number of collisions per second, right, is then linked to the rate, or not linked to it, it is the rate of the reaction. So if I keep, in this middle panel here, if I keep my enzyme, 5 enzymes per 100 milliliters, and I let this run for 30 seconds, right? And now I increase this to 1, 2, 3, 4, 5, 6, 7, 8, right? Say an 8% substrate concentration. Well, look, I still have 5 enzymes, right? What's the likelihood that these enzymes collide with the substrate? It goes up. It's increased, right? So if I have more likelihood, right, there's a greater likelihood of collisions in this same 30-second time period, right? This is key. So in 30 seconds and 30 seconds, right, the likelihood of collisions, right, I'm going to get more products made, in that 30 seconds, right, than I did over here in this first panel. So by definition, the rate is faster over here. I have more products made per that same time period. Okay? So what if I keep jacking up the substrate concentration, right? Now over here, I still have, again, my 5 enzymes, right, per 100 milliliters, so same concentration of enzyme. That's constant, the same 30-second time period here. Right? But now I have 2, 4, 6, 8, 10, 12, 14, 16, 18, I don't know, this is somewhere around, say, 30%, right, substrate. Well, what's happening here? I still got these 5 enzymes, right? So what's the likelihood that an enzyme collides with a substrate? Pretty high. But just because I have all these extra substrates around here doesn't mean that they're going to get turned over any faster. These enzymes right here, every single enzyme in this scenario right here is busy colliding with a substrate, busy converting it to product. And so what we say here is that the enzymes are saturated. We've reached this point where the enzymes are saturated, right? And the enzymes are working maximally. Right? They're working maximally. They're working as fast as they can. They are converting as much substrate into product in this given 30 seconds as they possibly can. So as soon as they are finished with this substrate, they move on to the next one, right? But they can only do it so many times. It doesn't matter. I could jam even more. I could make this 40%, right? And it's still not going to go any faster. Analogy: if you have a ferry boat that's bringing cars across a river or people across the river, the ferry boat can hold 100 people at a time, and it takes 20 minutes to go round trip, right? And there's 100 people on the dock, then in 20 minutes you can move 100 people across. But if there's 1,000 people on the dock, in that same 20 minutes you can still only move 100 people in that 20 minutes. The rate is constant. The ferry boat movement is working maximally, right? The ferry boat is saturated with people. Those other 1,000 people, those other 900 people that are sitting on the dock, they're going to have to wait, right? And that ferry boat can only move so many people at a time. Similarly here with enzymes, right? So if you followed all that, we're ready to move this onto then looking at what this looks like graphically, right? So here's our reaction rate, right? Or this would just be number of products made per unit time, right? Substrate concentration here. At a low substrate concentration, the rate is relatively low. I made, in that 30 seconds, I only made 2 products. Right? Only made 2 products in that, at that 2 products per 30 seconds here at that substrate concentration. If I increase the substrate concentration over here, those enzymes, right, will work, and they're going to turn over this many, they'll turn over a little bit more. In this center panel, as I keep increasing the substrate concentration, right, I'm seeing that my enzymes are becoming saturated, but not quite saturated yet. And so at this point, we are approaching this Vmax. We're approaching saturation. Not quite there yet, but we're approaching it. Right? And then once we're past this point of the graph, right? Once we're past this point right here, no matter how jacked up we have the substrate concentration, all these enzymes in the solution are saturated, and they're making as much product as they can per unit time. So if you bring this over here, what you would then find out is that you'd call that this rate right here is the Vmax. Right? This V, incidentally, is velocity, right? Collisions, moving. Right? So this Vmax is the maximum rate for an enzyme. Each enzyme has its own Vmax characteristic of it. And how do you know what those Vmaxes are? You have to experimentally figure out what they are. You could also look them up, but for what we're doing, it doesn't matter, right, what the exact Vmax is. But understanding that this concept of Vmax is there, this concept of enzyme saturation is the reason why this curve looks the way it does, right? Why you get a pretty much linear portion of the curve here. You get this approaching here. The rate is beginning to stabilize, level off, and then no matter how high I have that substrate concentration, because the enzymes are saturated, you're going to get the maximum product turned over per unit time. Okay? So here's a couple opportunities for you to practice putting all of that together. So if this was a graph of effective concentration of substrate on the rates, right? Label this axis here, label the axis here, and then what would this line represent? What's this line? What would this line? What would this line? What would this line? What are you going to do with all these? Why are these, this one here and this one and this one? Right? what would you do? What are all these? And then take that information, there's a blank set of axes, and what would you do? What does that mean? So this is an opportunity for you to kind of summarize the last 10, 15 minutes of me blathering on there. I'll give you a copy of this in class. Forget this toothpick ace thing over here for the time being, but this gives you an example, another place to practice some independent work. Here's a sample description of how you would describe what's happening, right? You could then practice, right, what if I changed the enzyme concentration? What if the enzyme concentration was elevated or lowered, right? This is the graph, right? If you jacked up the enzyme concentration, what would this look like? What's the what goes on this axis? What goes over here? And then your explanation. Same thing then for substrate and your explanation. Temperature, what would happen? pH, competitive inhibitors. We'll get to all these things in another one. Okay. This detailed enzyme kinetics tutorial is a link that you can click on. I'll put it on Blackboard as well. That is like super detailed if you are really interested. And that slide, I don't know why that's there for now, but there we go. Hope that was helpful.